page? Does anyone have
Have one?
blank?
Yes, but she's got 9 spots, so you can't have any.
How does that make any sense?
Doesn't. Okay.
Right. So, is anything coming from the course that you want to know about? Like before we start? Like anything theory related? No? Okay, I just go through the questions then.
Like any specific question?
Yeah, everything like related to the theory of
Oh, to anything.
Yeah. Was there anything in particular you find difficult?
Yeah.
Everything.
I'm sure that there's some bits that just mainly just algebra, but some bits actually requires a little bit more understanding. For example, one thing of course I find the bit about geometry more difficult than the other bit. Because there's so many more methods of doing the geometry questions.
Like the vector question.
Yeah, and then B, they're just harder to imagine because there's 3 dimensions in it, and it's harder to draw on paper. And I think that's the only hard bit about this paper I find. For example, question 1 is really just using, you just need to support the relationship that 3 to the power of x minus 2 is equal to e to the power of ln 3, which is the definition of logarithm, times x to the minus 2. And once you've spotted that, it's really a linear equation. We can deduce from that x is equal to x minus 2 times ln 3, and then rearrange, you should get x is equal to 2 ln 3 over ln 3 minus 1, and then just convert that into 3 decimal places. So anything you want to ask about this question? Good. And the second one is about the Trapezium rule. So when it's asking for 3 intervals, we obviously need the 2 endpoints, and then plus 2 more points in between. And we can see that 3 over 2 pi, 2 over 3 pi is really just 4 over 6 pi. And then we have the bottom limit 1 over 6 pi of cosec x. And cosec is just 1 over sine. And it's really helpful to just draw a table here and release all the values we need. So we always need the endpoint, so 1 over 6 pi. And we know that sine 1 over 6 pi is a half, so cosec 1 over 6 pi will just be 2. And the second one is 2 over 6 pi. We know that sine 2 over 6 pi is just root 3 over 2, and cosec would be 2 over root 3. And now we have 3 over 6 pi, and that's just a half pi. And sine half pi is 1, so cosec half pi is 1 as well. And finally, we have 4 over 6 pi. And you really need to support, you don't really need to support, you can just use your calculator, but it's the same as 2 over 6 pi, because sine theta is equal to sine pi minus theta. And you can support that 2 over 6 pi and 4 over 6 pi add to pi. And there will be 2 over root 3 as well. So we have all our values here. And then we just need to use our formula for Trapezium rule. So A is approximately equal to a half times the width of the trapezium. The width should be calculated as 2 over 3 pi minus 1 over 6 pi. over the number of intervals, 3. And so we calculate that to be 1/6 pi. And so this is meant to be a bracket. So the endpoints should only be counted once, but all the points in between should be counted twice. So 2 times 2/√3 plus 1. And then we'll come to the other endpoint, which should only be counted twice. And then just plug that into your calculator. So the thing to notice that the 2 endpoints should only be added once, but the things in between should always be added twice. Question 2 is more interesting. So sketch the graph of y equals cosec x equals to 1/sin x. When you're sketching this kind of composite graph, it's helpful to start with the graph you know well. So let's try sin x first. That's just a nice, well, that's meant to be more rounded off. But anyway, it hits 0 at pi, and then it hits 0 again at 2 pi. And it makes sense that you do the when you do the inversion, when the graph hits the when the graph hits 0, it should be infinity, because 1/0 is not defined, and we'll end up with shapes like this. Where this is pi, and this is 2 pi. And then the question is asking, how does the sketch help us in knowing whether it's an overestimate or underestimate? Well, it will always be an overestimate. It doesn't matter how many intervals you take, because if you join any 2 line segments on the graph, you'll see that it always lies above the actual graph. It doesn't matter which 2 points you choose. You can do that, or you can do that. Well, the deeper reason behind this is because it's a convex function. In A2 terms, it means the second derivative is always positive, so the graph is kind of bending upwards, and that's why when you use Trapezium rule, it will always be a overestimate. Question 3 is really just simultaneous equations. When you have 2 unknowns, A and B, which are constants, and you are given 2 conditions on this polynomial. The first one is that 3x plus 1 is a factor, which translates into the condition that when x is equals to -1/3, this expression will give 0. So that's your first condition. And the second condition is that when the p of x is divided by x minus 2, the remainder is 21. And that simply means that when x is equal to 2, p of x is equal to 21. So we have a set of equations, 2 equations and 2 unknowns, and we can solve that to get A is 12 and B is -20. Question 4, parametric equations. Well, there are 2 ways of doing the first questions, but they're equivalent in principles. So when you parameterize the curve, you're introducing a new variable t. And how to get back from this parameterization back to x and y is given by the formula dy by dx is equal to dy by dt divided by dx by dt. And well, we then just simply differentiate using chain rule that when y is equal to tan cubed t, dy by dt will be 3 tan square t, and then we differentiate tan t will be sec square t, and that's dy by dt, and over dx by dt, and there will be minus sec t to the power 4 times minus sine t, and when you simplify that, you'll get, sorry, there's meant to be a 3 here, and you have sec minus 2t and sine minus 1t and tan square t, and that will just give you sine t as required, and hence show that equation of tangent to the curve at the point with parameter t is y equals to x sine t minus tan t. Also, what have we got here? We know that on the curve, the gradient is always equal to sine t. And we also know that at any point on the curve, its coordinate is given by this formula. So we have point is equal to 1 over cos cube t, tan cube t, and then we can set up equation that y is equal to mx plus c, and we know that we can express y as tan cube t, and we know the gradient is sine t. We know the coordinate of x is 1 over cos cube t, and we don't know about the constant. That's what we're trying to find out. And rearrange, we have tan cube is just sine cube t over cos cube t minus sine t over cos cube t is equal to c, and from there we deduce that c is equal to minus tan t. So we substitute everything back into the equation. We get y is equal to sine t x minus tan t. Okay. Question 5. Suddenly understand why saying throughout this question the use of a calculator is not permitted. Are you allowed a calculator normally?
Well, yeah.
Yeah.
And some calculators you can
Okay.
put that in the answer.
Oh, I guess that's why, but it doesn't really help. But if you do it by hand, I think it might be quicker. For example, in the first question, given that z is equal to 1 plus I, find w giving you answer in the form x plus iy, where x and y are real. Well, when you're doing the conversion questions, if you're not that sure, you can always do the trick where you write out x plus iy, and remembering that x and y are both real, and you equate that to w, which is equal to z plus I z plus 2, and you substitute the value of z in is equal to 1 plus 2i, I minus 1 plus 2, and then you solve for the real and imaginary part of this expression, or you can just simplify this expression directly. And what we need to do is obviously time the top and bottom by 1 minus I. So on the bottom, you'll get 1 plus I times 1 minus I. I'll give you 2. And then on the top, you'll have 1 minus I plus 2I minus 3I times I over 2. And that will give you 3 over 2 plus I over 2. And given instead that w equals z and the real part of z is negative, find z. And now it just become a quadratic equation in a sense. So in the beginning we have w is equal to z plus I over iz plus 2. And in question 2, we translate that into z is equal to z plus iz plus 2. And we then get iz squared plus 2z is equal to z plus I. And rearrange a little bit, we get iz squared plus z minus I is equal to 0. And we just treat that as any ordinary quadratic equation. So we use the quadratic formula, which tells us that z is equal to minus 1 plus or minus the square root of 1 plus 4i times I over 2i. And simplify, we get that expression. And because we're told that the real part is negative, and because we can cancel out the I on the second part of the answer, we have to choose the negative root. So that will be z is equal to minus root 3 over 2 plus minus 1 over 2i. Well, you can simplify the second expression further to get a half I, which is closer to the form in the question. So any questions on the first half of the sheet? I think like all the questions is pretty much just solving equations that's either quadratic or linear. So it's mainly just algebra. And if you can keep track of what you're doing, you should all be fine. Question 6. Now we have a integral equation where you integrate from 1 to a, then 2x dx, we get 1. Well, when you see expression like this, we know that we haven't learned any method to integrate ln of x directly. So if there's no direct method, we should try other integration method, and the only one once we know is either integration by substitution or integration by parts. And here we should use integration by parts because we know very well the derivative of ln 2x is just 1 over x. And so let's try that. So it becomes the expression evaluated at a and 1 minus integration from 1 to a x 1 over 2x 2 and that would give us a ln 2a minus ln 2 minus the integral from 1 to a of 1 dx, and that's equal to a ln 2a minus ln 2 minus a plus 1, and we're told in the beginning that this expression is equal to 1, so we can just rearrange that to get the expression we want, which is a is equal to a half exponential 1 plus ln 2 over a. So once we have this iteration formula, what we can do is that we can choose some sensible values and then plug it in. So for example, we can try a0 equals to 1 and then plug this expression into a calculator. You'll get a1 is equal to something else. And just bear in mind that you need to record your values to 4 decimal places. And so you just do this for a few times. And eventually, it shouldn't be before too long, that the iteration will settle down to a value that's around 1.94. And that should be your result. Question 7. So here we have a differential equations. We have a variable R, the revenue per year in $1 million, and X, which is what's X stand for? So X is the rate of tax and R is revenue. So now we have a relationship between revenue and the rate of tax. And I guess the interesting thing to see is that firstly, there will be a point where dr by dx will be 0, which means that, for example, if x is 0, what would happen? Well, if x is very small, the right-hand side will be very big. So the rate of increase of r will be very big. But as we increase the value of x, you come to a point when 1 over x is roughly about 0.57, and at which point you can't further increase the value of x, because then you can't cross a stationary point, so to speak. And apart from the differential equation, we're given a point where x is, when x is 0.5, I is 16.8. Because we can do separation of variable, this is enough for us to solve the problem. So we have dr by dx is equal to r 1 over x minus 0.57. And really, you should spot straight away that the thing in the bracket is only a function of x, and this thing is only a function of r. So when you can separate the two variables, you should just divide over. So you have 1 over r dr by dx is equal to 1 over x minus 0.57, and integrate both sides with respect to the differentials. We get ln r is equal to ln x minus 0.57x plus c, where c is the constant of integration, so r is equal to x e to the minus 0.57x plus c. And here we're just plugging this condition that when x is equal to 0.5, r is equal to 16.8. And that can help us determine that c is equal to 3.8. So r is equal to x times e to the power of minus 0.57x plus 3.8. The second part of the question asks, this model predicts that r cannot exceed a certain amount, find its maximum value of r. So, well, we've just found out a formula for r, that r is equal to x to the power of e to the power of 0.57 x plus 3.8. And you might think that to find the maximum of r, all we need to do is differentiate this expression and find the stationary point. But that would be too much trouble because we're given a formula for the derivative of r in the first part of the question. And it's really obvious to see that this will equal to 0 when 1 over x is equal to 0.57. So that gives us the answer straight away that when x is equal to 1 over 0.57, dr by dx will be 0. And evaluate r at that point, it gives you the maximum value of r. I mean, there are a few interesting things you can say about this model. For example, you can go back and try to sketch the graph. And the thing to notice that this differential equation is not linear. So a lot of quite interesting things can happen. Question 8. By first expanding sine 2 theta plus theta, show this formula. And this again is just algebra. And I would really recommend memorizing this formula by heart. For example, the addition formula for sine is just sine 2 theta cos theta plus cos 2 theta sine theta. Or even if you can't memorize them, they're in the formula booklet, right? So you can just look them up. And we'll do that again. So 2 sine theta cos square theta plus cos squared minus sine squared theta sine theta. And that will be 2 sine theta 1 minus sine theta plus. Actually, I should have expanded this in sine only, but it's not a big deal. And that will give you 2 sine x minus 2 sine cube plus sine theta minus 2 sine cube. And that gives you the answer of 3 sine theta minus 4 sine cube theta. and show that after making the substitution x is equal to 2 times theta over root 3, the equation x cubed minus x plus 1/6 root 3 equals 0 can be written in the form sine 3 theta equals to 3 over 4. And I think what the question is clearly implying that the equation over here can be written in the form here, and then we can use the identity we just proved to make it a much easier equation to solve. Because compare these two equations, you'll see that this equation is a cubic equation, and we know that cubic equations are hard to solve. We haven't learned any formula that can solve them reliably in A2. But this equation, well, we still don't know how to solve by hand, but we have the calculator for that. So it's easier to solve the second one than the first one. So let's make the substitution first. So it will be 8 sine cube theta over 3 root 3 minus 2 sine theta over root 3 plus root 3 over 6 equals to 0. And we want a 4 in front of sine cube because in the formula we have a 4 in front of sine cube. So let's just divide everything by 2 and times everything by 3 root 3. Maybe times everything by minus 1 as well. So we get minus 4 sine cube theta plus 3 sine theta is equal to 3 over 4. And we notice that the thing on the left is basically sine 3 theta. And because of this identity here, we can solve this. So 3 theta is equal to the inverse of sine 3 over 4. So theta is 1 over 3 sine inverse 3 over 4. And then we plug sine theta into the original expression. And we should then get 3 answers out of that. In terms of gradient, there will be 0.322, 0.799, and minus 1.12.
Can I ask a question?
Yeah.
How do we know, so like how many values there are going to be? Because some of them repeat, and how do we know when to stop?
Okay.
In terms of when we get our 3x values. Like how do I know that after 0.322 and maybe after 0.799, I have another one to find?
The thing that you have 3 values here is not because the roots repeat. When they repeat, for example, sine 1 and sine 1 plus 2 pi will be the same thing.
Mm-hmm.
So when we plug that back into the formula, x is equal to 2 sine theta over root 3, we still get the same thing.
Yeah.
But the reason why we get multiple roots here is because we didn't solve an equation for sine theta, we solved the equation for sine 3 theta. So even though sine 3 theta and sine 3 theta plus 2 pi will give you the same value.
Mm-hmm.
When we divide them by 3, so we get theta and theta plus 2 pi over 3. And you take the sum of them, they are obviously different. And also we can have a sine of pi minus 3 theta. So the reason why we get three values is because although the three things in the brackets give you the same value of sine, but when we take them out and divide them by 3, they give you different values when you take the sine again, and that's why you know when to stop.
So is it so sine 3 theta will give me 3 different values? Or is that like always the case? So if I had sine 2 theta, would I get 2 different values?
Potentially. Well, I think I'm not sure about if there's a general relationship, but every time you can determine for yourself, because I suppose you're right, actually.
So, for example, like if you have a look at the sine curve,
Yeah.
you're always choosing these values, right?
Mhm.
And as soon as I realize that they're repeating, I can stop.
Yeah.
Okay.
Okay, let's just think about, is there a general relationship when I think it could be onto something here, because in essence, sine the period of sine 3 theta is 1/3 of that of sine theta. So you will have
3 different values.
two more values in the same interval, and that makes sense. Yeah.
But for sine 2 theta, you'll only have 1 more value.
Yeah, because so for example, sine 3 theta it repeats itself every 120 degree, but sine 2 theta repeats itself every 180 degree, and sine theta repeats itself every 360 degree.
That makes sense.
Also, we can do it like explicitly. So so as I said before, 3 theta over 3, and 3 theta plus 2 pi over 3. And in general, unless they're very special values, these two will give you different signs, and so will 3 theta plus 3 pi over 3. That is equivalent as this value here. But then if we do 3 theta plus 4 pi over 3, something interesting happened, because that's equal to theta plus 3 over 4 pi.
Because you're getting, well, 3.
Yeah, and this is theta plus 3 over 2 pi. And when you take the sine of these two values, they'll be the same actually. Because they they differ by 1, 2, 3, 4.
Well, that's a multiple of the other one, isn't it?
No,
4 pi.
make sure I get this right. So let's make some examples. So I think there will be exactly the opposite. And although that is the case, okay, so and what I'm trying to show here actually is that after a certain period, the roots do start to repeat, and that's when you know you need to stop. So sorry, I think I've confused you guys a little bit here. Let me just start again. Okay, hope I can get this right this time. So in question 2 and 3, we're solving a equation regarding sine 3 theta, but for the definition of x, we're only using the equation of sine theta. And when we solve a value of sine 3 theta is equal to 3 over 4, we know that sine 3 theta plus 2 pi would work, and sine 3 theta plus 4 pi would work. We're just using the periodicity of sine. Also, sine 3 theta plus 6 pi would also work. And let's divide everything by 3. The first one would give you theta plus 2 pi over 3. The second one would give you theta plus 4 pi over 3. And the third one gives you theta plus 2 pi. And obviously we have the original value of theta. And we know that theta plus 2 pi over 3 and theta plus 4 pi over 3 give you different signs. But this guy here, theta plus 2 pi, when you sign that, it gives you the same value as the original theta.
Because
so that,
it's a multiple.
Oh yeah, not because of multiple, it's because because sine is 2 pi periodic. So
Oh,
sine theta and sine theta plus 2 pi will give you the same thing.
okay.
So yeah, that's why there are only 3 roots in this case. So any more questions? I think in exams, if you have time, obviously you can check for the general case. But sometimes you can sort of just convince yourself that you found everything, because if you find more than 2 repeats after a few attempts, it's not really worth it to keep going. Okay. Question 9. So express f of x in partial fractions. Well, this is again just quite a lot of algebra, and it's actually quite easy to get around. So what we want is that we want to write that as a over 1 minus x plus b over 2 minus x and plus c over 2 minus x square. And when we get the expression on the right-hand side, we recombine that again and equate the coefficients of different powers of x. And then we'll get a is equal to 2, b is equal to -1, and c is equal to 3. I mean, I could try to do this now, but it's going to be a lot of algebra. Do you guys want to see how it works out? I mean, even if I do it, I can make quite a few mistakes as well. And there's really no tricks to it apart from, yeah, just be careful. Okay. Hence obtain the expansion of f of x in ascending power of x up to and including the term in x squared. So I guess the second part of the question is really telling you how doing partial fractions might be useful. So if I just tell you expand f of x in ascending power of x, what you would do is you would take out this thing on the top, so that just stays the same. And then you have to expand 1 minus x minus 1, 2 minus x minus 2. And, well, it's just really hard to do that in one go. But when you have broken things up into 3 nice looking fractions, it will really help you in this kind of binomial expansion. So you have 2 over 1 minus x minus 1 over 2 minus x plus 3 over 2 minus x squared. And the really important thing here is that when you have the negative power expansion, like 2 plus x to the power of minus m, you need a 1 in there pretty much. So you want to change that into a 1 plus x over something to the power of minus n times a constant. So let's see how that works in practice. So the first term is 2 times 1 minus x to the minus 1. The second term, we can write that as 2, 1 minus x over 2. And the third term, we can write that as 3 over 4, 1 minus x over 2 to the power of 2. And let's just make that clear. Minus a half, 1 minus x over 2 to the power of minus 1, plus 3 over 4, 1 minus x to the power minus 2. And at this stage, you can just plug in the formula. So 1 plus x to the power of minus n is simply 1 minus nx plus 1 over 2 m plus 1 x squared plus plus 1 over n factorial minus 1 to the power of n x to the power of n and n plus 1 n plus 2 and okay. And in the end, you'll find this expression to evaluate to be 9 over 4 minus 2x plus, wait a second. Is this what you got in the end?
I got 9 over 4 plus 5.2x plus 39 and 16x squared. Okay,
I guess that just shows you how easy it is to make mistakes in this kind of so I just realized it doesn't add up. It's a lot of calculation, but really there's nothing, there's no deep theory behind it. Let's go to question 10. So the line L has equation so there are really quite a few ways of doing this kind of questions, which is quite common for geometry questions. So let's draw a graph. So we have, we call this R. And what we know about R is that it passes through the point 4, -9, and 9. And it has a direction vector -2, 1, and -2. And also A has position vector 3, 8, 5. And show that the length of the perpendicular from A to L is 15. Well, personally, I think the easiest way of doing this question is to say that the perpendicular must have a direction vector that's perpendicular to the original line, because that's just the definition. So, but how do we find the perpendicular line? Well, let's just find the general representation between a line between a point on the line and A. So in a crude way, let's write A minus R, and that will give you minus I minus plus 17J, and let's do 5 minus 9 is equal to minus 4K, and then minus lambda minus 2I plus J minus 2K, and rearrange that to be minus I. Wait. So we now have an expression of a line segment that's between a point on the line and A. And now we want to choose, it's very important, the parameter lambda, such that A minus R dotted with the direction minus 2, 1, minus 2 will be 0. And we then find that we can solve this equation to get lambda equals to minus 3. And we plug this back into the expression and find that the line segment is equal to length 15. So let's just go over the idea again. So we first find a general expression between a line connecting a random point, let's say B and A. And we then change the position of B by varying the value of lambda such that AB is perpendicular to R. And if AB is perpendicular to R, then AB must be the perpendicular from A to L. Okay.
Can I ask something?
Yeah.
So when we did A minus R, we got
so this expression over here.
And that is equal to the direction vector from A to R? Because we dotted it with the other direction vector, which...
Yeah, that's the idea, yes.
Okay, but how does A minus a line give us that segment?
Sorry, I haven't been clear. So L is the line.
Yeah.
And R is the collection of every point on the line. So when I said A minus R, R is a point on the line, which is determined by choosing a value of lambda. So R
Okay.
is really a point, L is the line,
Okay.
and L is made of a lot of different values of R, and that's achieved by changing this parameter lambda.
Okay.
So really, it kind of combined all the things we saw before. So this is it has a parameter, and every point on the line is specified by this parameter lambda.
Okay.
And then you use the idea that when it's perpendicular to the line, you must give a zero dot product.
Yeah.
Okay. The line L lies in the plane with equation ax plus dy minus 3z plus 1 equals to 0. And this question also has a few different ways of doing it, which relies on dot product and stuff. But really, when you see an equation with two unknowns, let's just first try to find how many equations we can make out of the known condition. And what do we know about the line? We know its equation, that R is equal to 4i minus 9j plus 9k plus lambda minus 2i plus j minus 2k. Well, if we already know the equation of the line, so how about let's try to plug in a few points. So let's set lambda equals to 0. We get a point R is equal to 4 minus 9, 9, and lambda equals to 1, R is equal to 2 minus 8, 7. So saying that the line is on the plane, or the line lies in the plane, is basically saying every point on the line is also on the plane. And we have 2 points here, and we have 2 unknowns here. So that gives us 2 simultaneous equations for 2 unknowns, and that we'll be able to solve the problem. Yeah, and I think that's the like the best way and the quickest way to do it. So any questions? I think the last one is a lot harder than the rest of the paper because you haven't really done much geography in school maths. We all good?
Yes.
Good. And could you just show me how to turn this off again?
Yeah.
Also, I think we need to save the working as well.
Yeah. And then just go.
Like, because we're gonna do it, like, in a, like,
And then go to the Google Hangout.
I'm gonna try it again because I